Good morning.
Good morning, sir.
Good morning. Good morning. Yeah. Let us wait for about 5 to 10 minutes. I believe that more people will join. Yes, already there are many people have joined. So, well, I think since gradually people are participants are joining, I think I can start recalling what we have done already, so that after all right, so there are almost 200 people online. So let us start recalling what I have done, so that other people will come and catch up with what's happening. So let me share my slides. In fact, first let me quickly share my slides, and then we will go to the uh, this Qiskit and QSim workbook, and so that we will be able to run some things. Just one moment. Yes, so very welcome to everyone, and we are starting the second week of today's of our course, and our goal is in this course to understand the basics of quantum computing, and also the how to write uh, codes on the simulators. All right, so let me go to the slides again to give a quick recap of what we have already done. And here, these are my slides, and I think Jyoti has already shared these slides with you, and if not, they will be a good morning. Yes, they will be sharing. He will be sharing the slides with you again. So we started with this introduction. We talked about what are qubits and all, and by now we know what are qubits. So if we want a recall over here, I will include one slide here. So if suddenly someone asks me what is a qubit, so I will say qubit is a quantum state, and a single qubit system is a quantum state that can be specified by two complex numbers whose modular squares equal to 1. So typically a single qubit state will be written in this way: get psi, this is read as get psi, and this is a pair of complex numbers a and b. So a comma b are complex numbers with a property that mod a square plus mod b square equal to 1. And if a is a complex number of this type, like probably alpha 1 plus I times alpha 2, then, or let me define notation, it is not a good notation. So how do I write a? If a is, let us suppose, x plus I times y, and then a conjugate is x minus I times y, and mod a square is a into a conjugate, which is x plus I times y, x minus I times y, that is equal to x square minus ixy minus iyx plus y square, getting cancelled. So I've got x square plus y square. So this is essentially class 11, class 10, 11 stuff. So we need this. So this is a qubit. All right. Then what we learned is that it is possible to create a qubit in any, this is a qubit state. This is a single qubit state. A single qubit state. All right. Then what we learned is that I can create a single qubit state. I can create, in fact, many single qubit having the same state. But if I want to read, so reading is measuring. Reading is equivalent to measuring. So if I want to measure a single qubit state, then I can't do that in the classical sense. What I will be having is that I will be carrying with me an orthonormal basis, and measurement will mean that the qubit will be transformed to one of these two possibilities, and that will be my measurement result. I can note it down. I have not shared my screen. I have shared my screen. Wait a moment. Is that so? Someone said I'm not, my screen is not shared. I will share it again. Can you see my screen?
Yes, sir, your screen is visible, sir.
Okay, all right. Yeah. Indrajit Kundu has raised a hand. So I can, if Indrajit Kundu quickly asks a question, I can answer. Indrajit Kundu, you raised hand. Devesh Kumar has raised hand, but people are raising hands, but they are not asking any question. So, oh, sorry, sir. No problem. All right. See, the third axis No, qubits are not getting stored actually in the sense. I mean, like you can create a qubit, so you have to store it very. We can only store a qubit for a very short time, very, very short time. If Jyoti is online, Jyoti will tell how short the time is. But if you have to have an elaborate device to store isolate and store a single qubit or a very few qubits. So we are not talking about the right now. We are not talking about the uh, physical implementations. So we did not. I did not say that we cannot store. Devesh Kumar is asking that if we cannot store, then we cannot measure. I did not say that we cannot store. I am saying that you can create a qubit and retain it in that particular state for a very short time. It may be some, I think, some milliseconds or like that, or microseconds. I am not absolutely uh, specific about the particular time. So you can only keep the qubit for that long, and within that you have to do the measurement and all the operations and everything. So that is the point. All right. So you can measure this. Whenever you are measuring a qubit, you are coming with a orthonormal basis with two basis elements, basis vectors, and then so let us suppose this is one vector and this is the other vector. These are orthonormal, so you know that inner product u bracket uu is 1, inner product bracket u part is 1, and inner product u bracket u part is equal to u part u is equal to 0. So this is orthonormal state, and then once you do that, suppose you are measuring the qubit size with respect to this measurement, your outcome will be either this vector or this vector or this quantum state or this quantum state, and then the probabilities will be measured by the square of the inner products. So bra u psi get whole square. This is the probability that you will get this vector as the measurement outcome, and this is the probability that you will get the perpendicular of that vector as the measurement outcome. So these are all normalized vectors, and that's what you are going to get. So that's what we did in the last class. So if there are questions, I'm stopping for 2-3 minutes. If there are questions, please type them, and I would be happy to answer them as far as possible. Kapil Prajapati. I am MSc Physics student at IIT Gandhinagar, and I am doing project. Yeah. Let me see the chat. So I saw a message from Kapil. I can't find it again. Sanjay Rai said, what is the new notation you have used here with you? Oh, u perpendicular we sometimes write as, this is u perpendicular. So it is a vector perpendicular to u. So that's the notation. Madhuri says that she has not received the PPTs and recordings, that will be made available. Is the probability square complex conjugate? Yes. Whatever you and Jyoti have explained is clear. Thank you. Kapil, I am MSc Physics student at IIT Gandhinagar. I am doing project in general relativity. So is it fine for me to take this course? Can anyone tell me about this? I do not know. You can measure the qubit, then qubit collapsed. Yes, of course. How many ways to measure without? You can't measure without affecting the quantum state, yeah, in general. If you cannot store with, there will be measurements. So these questions are already answered. Now, Riptorshi Rai says that, sir, can you please explain the global phase and the relative phase once again? How? Yeah, Diptorshi, I will keep this in mind. Right now, I will explain this sometime later, because we are not really, we won't need it really. Chorwani also says that, could you please explain? I will remember you, both of you, and I will explain that, but let it be some other time. It's so Chorwani and Diptorshi. Yeah, qubit transformed from quantum state into classical state. You can call it a transformation. Yes, maybe. Yeah. Okay. See, global phase and relative phase, the idea will be clear only if we do some small problems. So I have no problem. We will discuss these problems, but I think that there was a raised hand some time ago. Now, Srinivas says, sir, can you please take questions at the end? This is the way whole flow of lecture is being broken. Sure, Srinivas, I will take the questions at the end. I just wanted to check whether everyone is on board. Now, let us move on. All right. So see, we are coming back again here. And then another thing that I told you, let me write over here. So insert another slide over here. So what I told you is that, look, I cannot, what I know that is that I cannot really, I cannot read a quantum state without disturbing it, but I can do something, and that something is I can transform a quantum state. We can transform a quantum state. But again, we cannot transform it any way we like. We cannot transform it any way we like. We can transform it by using a unitary operator. We can transform a quantum state using a unitary transformation. Now, what is a unitary transformation? So if U is a transformation, now suppose then it can be written, suppose it's a single qubit transformation, a transformation on the single qubit state space, then it can be written as A11, A12, A21, A22, A21, A22, and the conjugate transpose, this symbol is called dagger. I've grown to like it actually. This is the dagger. So this is U dagger. So if you take U dagger, then U dagger is A11 conjugate, wait a moment, A22 conjugate, A12 conjugate, sorry, A21 conjugate, and A12 conjugate. So you have to take the transpose of the matrix and take the conjugate of complex conjugate of all the entries. So then you get U dagger. And if it so happens that the inverse of this matrix is equal to U dagger, so of course needless to say that these matrices are then invertible. Now, if the conjugate of a matrix is if a conjugate of a matrix is U dagger, sorry, if the inverse of a matrix of a particular matrix is this is called the conjugate transpose adjoint of the matrix, then it is called a unitary matrix. This is the property of a unitary matrix. Now, what we noted in the last, almost at the end of the last session, is that we noted that so what we noted in the last is that see if you have a unitary matrix, wait a moment, there was a shot. So we noted that the standard transformations, there are 4 standard transformations. Those are called Pauli gates. So one is X, of course, one is I, that is the identity transformation. One is I over here, so which is identity 1001. Then I saw X, that is 0110, and then there were 2 more, Y and Z. Y is this and Z is this. Z is 100 minus 1. So let us see what is Y. Let's come here. Just one moment. I keep on forgetting what is Y. There's a reason for that as well. So Y, please remember 0, 1, 1 minus 1. Yeah, 0, 1, 1 minus 1. Now, it can't be. Minus 1, yeah, 0, 1 minus 1, 0. That is my Y. And this is my Y because in Riefel's book, she uses this Y. There is another Y actually. Sometimes standard notation is different, but that we will come later. So wait a moment. Yeah, I was here. So see, this is 0, 1 minus 1, 0. So 0, 1 minus 1, 0. Yeah. Yeah, so that's that. So you have got, we call that Y. Now we also saw that you can write identity matrix in this way. That is get 0 bra 0 plus get 1 bra 1. X is equal to get 1 bra 0 plus get 0 bra 1. Y is the similar way minus get 1 bra 0 plus get 0 bra 1, and Z is get 0 bra 0 minus get 1 bra 1. So we'll find that you write like this. But there is another transformation that is very, very important. That is the Hadamard transformation, that is 1, 1, 1 minus 1, which is equivalent to 1 over root 2, and then get 0 bra 0 plus get 0 bra 1 plus get 1 bra 0 minus get 1 bra 1. So this is Hadamard. So this is essentially what we did in the last class. And after that, I will now go to, I will talk about the 2-qubit systems. And then we will move on to our the workbench, that is the portal, to see how to implement them. I have shown some time ago also, but we will see that again. Of course, we will keep on seeing that. Now we are coming over here. So this is what we have done. Yeah. Kapil writes, yes, of course, is 0I minus I0. But if you see that if you take this I out, then it becomes I times 0, 1 minus 1, 0. And the book I am following, that is she, Riffel and Polak writes is like that. So I keep on writing like that, and Jyoti keeps on writing the other way. Yeah, so that's it. All right. Now see, the question is about 2-qubit states. Now from here we are so from here we are like we have a new topic. All right. So now see, the point is, let me as usual introduce some extra slides so that I can talk to you. See, the point here is that we have seen a single qubit state. Now we are talking about 2-qubit states. So from single qubits to what's 2 qubits. Now suppose we have got one qubit like this psi, which is equal to, let me see, what I'm using. Okay, I'm writing phi1 and phi2 here. So let me stick to my notation over here. So suppose I write this as capital phi1, which is equal to A ket 0 plus B ket 1. And suppose I write this as capital phi2, which is equal to C ket 0 plus B ket 1. Now, these are two separate single qubit states, and I am talking about 2-qubit states. Now, what we will do? We will say that what is so great about it? Like if you write two states side by side, if you write two single qubit states side by side, then that's the state of that 2-qubit system. Let us start by this, and then we will like see what happens. So let us start that it is like this. So I am writing these two states side by side and calling that a 2-qubit system. So this is the state space of a state of a two qubit system. This is not, there is no problem there. So when we start like this, and suppose I ask that I have to measure them. So suppose I want, so what are the, suppose I say that I am measuring this qubit by using the usual orthonormal basis, that is ket 0, ket 1. And I am using this by using a usual orthonormal basis, that is ket 0 and ket 1. So what are the possible measurements? What we should be having? All right, so think about it. Okay. What are the possible measurements that we measurement results? Of course, I mean, I have got two for the first qubit and 2 for the second qubit. So the measurement results, the possible measurement results are the possible measurement results are, I can get this. So first qubit at gate 0, second qubit at gate 0, I can get this. I can get this, and I can get this. So there is no mystery about this thing. I mean, of course, I mean, it will be something like this. Now, I may ask a question that what is the yeah, I have made a small mistake here, so I'll change it. Yeah. So this it is D. Yeah, it's of course it's D. And here also it's D. Yeah. All right, D. So that's it. So now the point is that if I'm assuming that these two qubits are kind of independent and they are not influencing each other, then the measurements are results are independent. And the probability that I will get 0, I will measure get 0 for the first qubit, that is of course mod a square, and the probability that I will get 0 for the second qubit, that is this. Now see the joint probability, since I'm assuming that I mean like they are kind of separate. So the joint probability is the product of these two. This is small x is a product. So this is equal to AC mod whole square. There is no problem there. This is complex numbers. Now similarly, here this is going to be, this probability is going to be this is square. This probability is going to be A B square. This probability is going to be BC square, and this probability is going to be BD square, not BD square. So there is no problem there. Now see that how I can kind of get this from some kind of algebraic operation. Let us come to this point. See, my phi 1 is equal to A ket 0 plus B ket 1. Phi 2 ket phi 2 is equal to C ket 0 plus D ket 1. Now see, this ket 0, ket 1 and all these things are matrices. So I can multiply them just as matrices. If I by chance do that, so I write them side by side and just choose to multiply and see what will happen. I get AC ket 0, ket 0. Then I get AD ket 0, ket 1. Then I get BC ket 1, ket 0. You may say that why I am multiplying. I'm saying that what is the problem? Because ket 1, ket 0, they are matrices, and I'm using all the rules of matrices, matrix multiplication. So there is no problem. It's quite valid. So if I'm writing this, now see this is another kind of expression. Like I am seeing that I can actually write any two qubit system as kind of linear combination of things like this, two qubit states like this. Okay, and if you look at the coefficients, as far as I've seen, these coefficients are also kind of normalized. I mean, like what if I ask that what is the probability of observing ket 0, ket 1? It is mod AD square, and that is also something that I obtained from direct analysis. So somehow this notation works. Now I would like to go one step forward, and I will introduce a product that was introduced much before all the quantum mechanics and all that. Yeah, wasn't it, Jyoti? Kronecker was much before. Yeah, so there was one person called Kronecker. Personally, I like Kronecker very much, and he introduced one product like this. If you have a matrix, let us say alpha, beta, suppose a vector like this, and another vector gamma, delta, and this product is called the Kronecker product. The result of this is this: alpha times gamma delta and beta times gamma delta. And therefore, this result is alpha gamma, alpha delta, beta beta gamma, and beta delta. This is the result. And I will use Kronecker product for all these vectors. All right, so what is Ket0, Ket0? Ket0 is 1, 0. Kronecker product, because see, Ket0 is 1, 0 and Ket1 is 0, 1. If I take the Kronecker product Ket0, Ket0, so it is 1, 0, 1, 0. You will see that this is 1, 0, 0, 0. If I take 1, 0, Kronecker product 0, 1, if you patiently do it, you will see that it is 1 times 0, 1 and 0 times 0, 0. 0 times 0, 1. And so therefore, this result is 0, 1, 0, 0. Similarly, 0, 1, Kronecker product 1, 0 will give you 0, 0, 1, 0, and 0, 1, Kronecker product 0, 1 will give you 0, 0, 0, 1. So these are indeed getting mapped to these kind of things. AC 1, 0, 0, 0 plus AD 0, 1, 0, 0 plus BC 0, 0, 1, 0 plus BD 0, 0, 0, 1. And therefore, this is AC, AD, BC, BD. You see that somehow, if I interpret these things as Kronecker product of matrices, then naturally I am able to embed this thing in a 4-dimensional space over complex numbers. So that is a peculiar thing that is happening. And so I can say now that under this interpretation, these vectors, these things, these objects can be thought of as the basis vector of a 4-dimensional space over complex field, and I have got a vector in that space, and such that the mod square of all the sum of mod square of all the coefficients are adding up to give me 1. So what I have seen that that I take two quantum states side by side, I can map this quantum state to a state space like this. This is the structure of the state space. And if you go here, that is exactly what I have written on my slides. So exactly what I have just now explained. So you will get all the data typed out by me some time ago, but I just worked out this thing again. All right. So I have got a 2-qubit state like this. Now, the question starts here, that suppose I have got a quantum state like this. Yeah. So see, suppose I am writing like this, or alternatively like this. They are same things. So suppose I am writing like this. Suppose this is now what, this is what, this is what. So this is essentially the vector 1 0 0 over the complex numbers. This is 0 1 0 0. It is 0 0 1 0, and this is 0 0 0 1. So now you know how to interpret. If I say that I consider a 4-dimensional space over complex numbers, and I consider vector there, and such that this condition holds. So here, see, like, I'll probably put in green, so that this condition holds. And now I will ask a question, that is it a valid 2-qubit state? And the answer is yes. We know that we can construct any vector in this space whose component square mod square equates to 1 is a valid 2-qubit state. Now, the point is that what was found out, that these states, there are plenty of states like this that cannot be written as that cannot be decomposed into two independent quantum states, and that is what we are going to discuss now. So we saw that if I get two independent quantum states, I can kind of map it to a 4-dimensional space over complex with certain things, and we identify the basis vector of that space and how to quickly get the basis vector. But then it opens up many possibilities. Then, of course, we ask a question that whether that is, I mean, we can do something more about it. Our answer is that, like, we are going to get something more interesting, and that's what we are going to do next. But before that, if there are questions, I mean, I think I've talked about 45 minutes. I think now we can have a short question answer thing with chat and all, and then we will move there. Okay, so Shorgani says that why do you need unitary transformation? That is a restriction that physicists have told us. Like we have to take unitary. And the Madhuri says that yes, Kronecker product equals to tensor product. Of course, it's a tensor product. I'm talking about tensor products. But tensor product, the name came much afterwards. I mean, like, Kronecker did these things much before. The Kronecker product is named after, well, thank you for this, Kingshuk Sarkar. Kronecker product is named after the German mathematician Leopold Kronecker, 1823-1891. Even though there is a little evidence that he was the first to define use, Kronecker product has also been called, okay, wave-pass matrix. Yeah. So thanks, Kingshuk. Okay. Indrajit Kundu asked, what is the geometric meaning of this Kronecker product? I don't know. Like, it itself is a geometric meaning to some extent to me. I don't know. Like, I mean, it is the meaning rather than I'm basically, it is the, to me it is the meaning of tensor product, but I don't know anything. Varsha Tiwari asks a very important question. Sir, is there any book which we can read, from which we can read tensor products? I would like to again see the tensor products are not very easy things to understand. Varsha, I think that Riffel and Pollack gives a very good introduction, short in within 1 or 2 pages. They talk about tensor product. I would say that's a very good starting point. Now, Kopil Prajapat asks that could you show the previous slide? I will show the previous slide a little later. The qubit is similar to bytes. Is there 1 byte, 4 bits, and like that? I will see two-state qubit is not really very similar to bytes, because if you have got bytes, this 8 bits makes a byte, but the number of states in which a byte can reside is much more restricted than number of states in which a 2 qubits will reside. I mean, we'll see that soon. Sir, we know Srinivas writes that a square plus b square equal to 1, and similarly this is 1, and how? Oh, you can directly check that actually. This is direct algebra. If you do complex numbers, you will check that. You will be able to check that. Will there be superposition between two states? We are coming to this like that once more. Once theorem 62 slides after question session. Yes, I will show slide 62 after the question session. Slide 62 after the question session. Dr. Kusumlata Agarwal asked that when the assessment of the course will start and how assessment will happen. We probably give some quiz kind of questions. Probably. So to obtain higher dimension basis vectors, we should use basic states. Yeah, we can get higher dimensional states like that. Now, Kingshuk, physical meaning of Kronecker product is multiplication of Hilbert spaces or basis spaces of Hilbert spaces. Yeah, okay, you can say that, but I will ask that what is a Hilbert space? So, I mean, like meaning of the Hilbert space or geometrical interpretation of Hilbert space, then that becomes another question. So, all right. Dr. John Peter says that tensor by Joshi agreed. Manasa Jayaprakash writes that how to visualize qubit states you have just described. I do not know. Can you share all these slides in our mails? Yes, of course, we will share the slides. All right, I think that now things are more or less all right, and then we will go to we have seen the single qubit. Wait a moment. We have seen the single qubit states. Now we have seen the gates also. Now what we have to see, let us come here after this. I had a request to show 62, slide 62. Yeah, this is slide 62. So this is what I worked out basically. And now the question is that how to all right. Wait a moment. So, sir, does Kronecker product the dimension of a vector? What does the Kronecker product of the tensor product increases? Yes, of course. I mean, if you take the Kronecker product, it increases the dimension of the vector space. Can you use QC for storing data, since you said the qubits cannot be stored? What is QC? So we can't store data. There are limitations in storing data. Okay. We will, Hilal asked about reversible circuits. We will be talking about reversible circuits soon. So, all right, now I'll not look at the chat anymore. So I have shown this slide, and now I'll come over here, and then I will kind of right, we will work out something. Let us see whether it works out nicely or not. So I will give an example of a 2-qubit state. Sorry, 2-qubit gate. So let me write down over here. So far, we have seen quantum gates that operates over a single qubit. All right, this is what we have seen. Now we will move on to describe a quantum a transformation that operates over a pair of qubits. Now we describe a unitary transformation that operates over a pair of qubits. All right. Now, what is it? So let me let me directly show the transform and how we write the transform. It is like this. This is one qubit x, and this is another qubit. Let us call it y, like this, and I will put a line like this, and I will put a cross mark like this, and we have to say what happens here. For that, I will list the effect of this transformation on the basis vector. So I know that this is a 2-qubit state. I have already told you that the basis vectors are like this: Ket0, tensor Ket0, Ket0, tensor Ket1, Ket0, sorry, Ket1, tensor Ket0, and Ket1, tensor Ket1. So this is a basis vector. So whatever it is, this is a linear transformation. If I can specify a linear transformation on the acting on a linear space, on a vector space over a field, and if I can specify its transformation on the basis vectors of the space, then I have specified the transformation completely, because I can then find out all the images of all the vectors in the field. So knowing this, I start my process, and as a compact notation, I will be from time to time writing this. They are the same things. This is just notation, or a semi-compact notation, dropping the tensor product symbol. I may be writing like this. All right. Now, my rule is like this. If the first qubit 0 corresponds to the first qubit state, and 0 that second, if you pass 0, 0, it will go as it is. 0, 0. If you pass 0, 1, it will go as it is, 0 1. If you pass 1 0, then the second qubit, so that if the first qubit is shift from 0 to 1, then the effect is that the second qubit state is flipped. So the result is 1 1, and if the first qubit state is 1 1, then the second qubit state is 1 0. So it's flipped. If you want to construct the matrix corresponding to this linear transformation, then it will be like this. So this linear transformation is called C naught. So I will use this notation. So this is C naught. The matrix corresponding to C naught. For that, I have to see this image. So see, gate 0 0, C naught of gate 0 0. So let's see. Let's write like this. C naught of gate 0 0 gives me gate 0 0. C naught of gate 0 1 gives me gate 0 1. C naught of gate 1 0 gives me gate 1 1. And C naught of gate 1 1 gives me gate 1 0. Now, as you know, I can actually write this thing is this essentially. If you want to be very, very particular, so we can fill in all the blanks over here. So this is essentially the matrix. This is essentially what happens. And so what is the matrix? You have to take the coefficients and construct a matrix and take the transpose of that. So the matrix corresponding to C naught is transpose of the coefficient matrix of this thing. So that is 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0. So this is the matrix corresponding to C naught if you have the basis in this order, particular order. All right, so this is C naught. Now we come to the next slide. All right. So if I start with gate 0 and apply Hadamard on it, and suppose here I am starting with gate 0 again, I've got 0 here, and then I apply Hadamard. So if I apply Hadamard, this state will be gate 0 plus gate 1 divided by square root of 2. All right, and this state goes like this. And then if I apply a C naught gate over here, let us see what happens to this one, like this. So what is the state that is entering this C naught gate? So I am now interested in this gate in particular. So see, I am just looking at this gate, the effect of this gate. And what is the quantum state over here? The quantum state is this. So the first qubit is this, gate 0 plus gate 1 divided by square root of 2. Second qubit is gate 0. So I can write the quantum state in a more expanded form like this. So it is a superposition of two states. One is 0 0, 1 by square root of 2 0 0, and another is 1 0, gate 0 1 0. So this is what is going in. So this C naught gate, this is a C naught gate, and this C naught gate is going to So this C0 gate is going to operate over these individual qubit states. If C0 gate operates over here, then the answer is this 1 by square root of 2 gate 0 0, because the first qubit being 0 is not, nothing is going to change over here. And if you on the next one, since the first qubit is 1 and the second qubit is 0, the second qubit is flipped, so you will get 1 1. So here this state is going to be 1 by square root of 2 get 0 0 plus get 1 1. All right. Now you will say, okay, what is so great about it? I mean, like, okay, let it be. What is the problem? I say, okay, there is no problem. What I've proved here is that I can start with 2 ket 0 states. I can always create 2 ket 0 state, and I can always apply a Hadamard gate on the first ket 0 state, make it in a superposition state, and then superposition of ket 0 ket 1. Then I have the, on the other qubit there you have the ket 0, and then you are applying a C0 gate over this combined 2 qubit states to obtain this one. Then I say that, look, this is a 2 qubit state, so let us try to find out its it's the states of the first qubit and the second qubit. So I would like to do something like this. This is very important. Please take note. So I will probably do it on with a different color. Let me choose a different color, not green. I think I'll use this color to make the thing more lively. Yeah, but oh, sorry, it's a little thicker side, right? So let's use this color, put it like this. Yeah. So see, I'll say that, okay, so this is my state, get 0 0 plus get 1 1, and suppose it is a combination of this state, get B1 tensor product, so it's always tensor product of C ket 0 plus B ket 1. All right. Now see, if I expand this, use the tensor product rules, so then I'll get something like this: AC ket 0 0 plus AD ket 0 1 plus BC ket 1 0 plus BD ket 1 1. And now, of course, if the right hand side state is same as the left hand side state, so they should be, I should be able to match the coefficients. So AC is 1 by square root of 2, AD is 0, BC is 0, and BD is 1 by square root of 2. So because of this first and last, for this first and last, it's first and the last equations, I know that A is not equal to 0, B is not equal to 0, C is not equal to 0, and D is not equal to 0. But then how are these two things equal to 0? And this implies a contradiction. So this contradiction I will write in red. A contradiction. All right. So the final conclusion is that I cannot write this extreme right hand step on the circuit as an ensemble of two separate quantum states. It is something else. And what happens for this state? is that let us look at the state closely. So for that, let us just use a little bit of space over here. This state, if the first qubit is measured to 0, the second qubit automatically is at 0. And if the first qubit is measured to KED1, second qubit is also KED1. So we know from physics, from experiments, that it is possible to create states like this. How to create by using a quantum computer, I have told that. But there are also physical processes that Jyoti will be a better person to explain. He will say how it can be stored. As I have understood that if you have, it's possible to combine what happens, photons, right? You can kind of do something with photons, two photons or something like that, and create a 2 qubit state. Not necessarily that. It's something else. The physics part, Jyoti will tell you. I am maybe like in the physics, I am not that much strong. So the point is that you can do something and create a 2 qubit entangled state. And these independent individual qubits can move very far away. But still they will remain in entangled state. And if you measure this one, then automatically the state of the other will change. So this is a very peculiar thing that happens in quantum mechanics. I will not venture to say anything more. This is called this is called an entangled state. All right, so I will tell this, I will highlight this and say no more, because entangles, these are really very complicated things in some ways. But from our side, we really don't have to worry about the physics, because we are interested in using these things for computations. So from our side, we have to see that how on a quantum machine we can create entangled states. All right. So I think I will stop my lecture now after I have done this, and we will go to our workbook and check very soon how to create entangled states. And also we will rework out these things, right? So let us take some questions now. So if you ask questions, okay. So I have a call firstly. Just one moment. Achha, okay. Okay, yeah. So, Swapnilas, what is the meaning of entangled? Dr. Kusumlata says physical significance of entangled state. Physical significance, Jyoti will tell. Jyoti will tell. Can you tell it now? I mean, like, can you give a lecture now after this one? Okay, we will first see the workbook, that how we are. Yeah. Nilotpal Vishwa says, can you repeat how you said that this set is an entangled state? Yeah, I will repeat it. Could you elaborate about C0 gate and what are the lines and dots and cross signify the symbols? Samarko Banerjee, thank you for asking this question. I can elaborate it to no end. All right, I will do that. What is the conclusion of this contradiction? Yeah. So Sonakshi Saha writes that what is the conclusion of this contradiction? The conclusion of the contradiction is that you cannot obtain this final state. So the point is that we started with a state ket0 and ket0, a 2-qubit state, which both the qubits are in a certain state. All right, so we know that I have 1 qubit in state ket0 and another qubit in state ket0. So I have got that 2-qubit state. What I did is that I applied the Hadamard transformation on one and then combined them. It's kind of, it's almost like punching them together. I applied a C0 there and it comes out. The resulting state is ket00 plus ket11 divided by square root 2. It is a valid 2-qubit state. But now if someone asks me, what is the state of the first qubit and what is the state of the second qubit? I can't answer the question. In order to answer the question, I have to write again, let us suppose that the first qubit is in a particular state, A ket0 plus B ket1, and the second qubit in a particular state that I don't know, but it is C ket0 plus D ket1. Then the combined state, as I told you, has to be what technically it is the tensor product of those two states or chronicle product, or like that. I do that, I punch them together and I get something like this over here. Whatever I get over here. Oh no, what happened? Whatever I get over here. So see, I'm like here. So I'll put a light colored thing. Yeah, okay. So whatever I set over here, so this is what I'm getting. So this state ought to be equal to this state. But if this state is equal to this state, then see, it is algebra. So how will I get the values of A and C, A, B, C, D? I will get the value. I have to solve an equation. Now, if I have to solve these 4 equations. If I solve these 4 equations, I am seeing that I am unable to assign any particular values to these things, because 2 equations tell me that none of these coefficients is 0, and other 2 says that at least 2 have to be 0. How can that be possible? So this means that although I started with a particular 2 ket0 states, I have arrived at a state which is 2-qubit states, which has a particular state as far as together. But individually, I cannot assign any quantum state to them. And this is exactly, if something like this happens, then we say that these 2 quantum states are in a, this is a 2-qubit entangled state. These 2 states are entangled. I cannot determine them individually. But all these transformations are reversible. So if you again apply a Hadamard and apply a C0, you will get back the original ket0. So you can entangle 2 qubits and you can again disentangle them by applying the inverse transformation of this particular gate. So that is what we get out of this whole thing. So let me see the chat again. Yeah, in Anmol says that, so if we can determine them individually, then they are not said to be entangled. Yes. Yes, the cases are physically different because the measurement values are very different. Because see here, that is the thing. Like if you measure ket0 first qubit, and if the measurement result is 0, then the second qubit is already set to 0. Similarly, if you measure the first qubit and if the measurement result of the first qubit is K1, then the second is immediate K1. So that is what we have. Yeah. Is this entanglement physical? Of course, this is physical. Preeti asked that whether it is physical. Yes, it is very much physical. In an entangled state, all the probabilities ABCD changed, or only the probabilities of one qubit changes with respect to the other? Actually, I just wanted to. It is a totally different state. I mean, like, just wanted to show you that you can't arrive at this uh, by using two distinct states. I mean, two independent states. I mean, like, you cannot write this in terms of that. So if we can determine them individually, they are not. So C0 changes the qubit. Yeah, yes, of course, but how it behaves like. Um, but how it behave like qubit? Q treats is Q treat. We are not looking at Q treat now. What happens when we try to measure just one of the entangled bits? I have told just now. I have to check that. Bhaskar Chakraborty writes that, so if we can computationally somehow pass a Hadamard basis and a state of our choice, and yeah, I mean, something like that, we have to check that. Okay, Prasad writes that while writing program on quantum computer, these all calculations need to take into account. No, we will write, we'll see. We have to, I mean, we have to do that on our back end of our brain, that this is what's happening. But for kind of doing the writing the quantum program, we don't have to do that. Uh, so I think we can get some 5 minutes break, and after that I will open my Qiskit account, and I will show you how we can create an entangled state. And before that also I will show you the syntax and all that of writing the quantum program. So just give me some 5 minutes and I will be coming back. I am back. And now Manas. Yes. Okay. So I will now go to the demo, stop sharing. I will now go to the workbench and I will demonstrate the this thing, and then after that I will so after that I will yeah, Jyoti will take over and Jyoti will also discuss these matters. Now let us come to the so let me share it again. And now this time let me share the Google Chrome. Yeah. Is it visible? Visible? Yeah. So this is visible. So there are two workbenches or kits. One is this IBM quantum computer and this is ours. It's QSim. We can log in on both. But I will start with this IBM thing here. How to access IBM quantum computer? Basically, if you write IBM diskit, so you will arrive here and no, it's not this. IBM Q. So if you write, oh, I wrote IBM A. If you write IBM Q, then you come to IBM Quantum. All right, and here we have to create an account, and that's only what we have to do. So once we have created an account, then we will be signing in. Signing in is over here. So if you sign in over here, then this is my account. So I am signing in. Password. Refuses to save my password. So I type in the password. I've typed in my password. Now we will come over here. So is it all right? I think. Wait a moment. I'll try to check the chat. Yeah. So let me keep the chat open so that we can kind of discuss and keep on checking what's happening. All right, I have the chat open. The password of QSim workbench and all done from the CDEC side, so you will get it from there. And here, Mir Yusuf is IBM Q is free, and QSim is also free. Yeah. So you will get, if you have not got the access of QSim yet, you will get the QSim access soon. So don't worry about these things. Now we will launch the lab. QSim is open source. All right. So we come over here. Now I have some, so you will see that there are many tutorials on Qiskit. QSim also there are tutorials, and Qiskit textbook, yeah, then quantum circuits and all. Now I will come to our programs. It's here. So you can create a, yeah, so this is the program. So it works just like the usual notebooks, like Jupyter notebooks and all. So now see the things that we have to do. Okay, so Abhirami says that to everyone, sir, could you please repeat the login? So in order to log in again, I have to log out once more. Let me do it one more time. So I have logged out. So I have to come to this page. This page is IBM Q page. And then I have to prepare I have to create an account from here, create an account. And after that, once the account is created, I do the usual login. All right, so I get the IBM Quantum Composer and IBM Quantum Lab. I propose that we use the Quantum Lab. So we can also jump back into one of our projects, but I'm not doing that. And there is an API token that we need to use if we are running the our code on the actual real IBM quantum computer. We are not going to do that yet. And after that, we will launch the lab. The lab is launched. Sumantokar asks that, do we have some repository on QSim? Yes, you will get, we will be posting many programs and all that. Yeah, we will get that. Okay, once I'm here, I go to my program. As usual, we have to open this like this. I think now it is clear how to start and see. Then we have to write these things. Just one more. Yes. So we have to write like this. So if you look at the comment is import Qiskit and call it Q for short, so we can construct, simulate, and run quantum circuits. In order to construct, simulate, and run quantum circuits, we need a Qiskit. So we'll import that and call it by the name Q, because we will be invoking it several times. So it is better to keep a single name, that's Q. So import Qiskit as Q. And as usual, import NumPy library and call it NP, so we can do maths. For doing maths, we need NumPy. So import NumPy as NP. So hence after, we will, if we want to call NumPy, we will call it NP. If we want to call Qiskit, we will call it Q. And then import the Python plotting module of matplot library and call it PLT. We can draw graphs. So we can draw graphs. So matplot library So matplot library, pyplot, and that's PLT. Now tell, so that's all right now. And then this is what we studied after this. This is quantum circuit. This is a class. This is the Qiskit's way of designing a quantum circuit. It takes two inputs, qubits and classical bits. So, which tells the circuit how many qubits and how many classical bits to use. So we see it over here. All right. So that is circuit, quantum circuit Q. C, Q is the classical number of quantum bits, C is number of classical bits. So now this is where I am doing the circuit, that Q dot quantum circuit. So Q is what here? Q is Qiskit. So within circuit, within Qiskit, you have the class quantum circuit, and you put this arguments, pass these arguments, right? 1 and 1. So 1 stands for the number of qubits, and the C stands for number of classical bits. See, if you do this. So what is the problem? The problem is that I have to run this thing first. I've run it, and now I'll run this one. It has run. Now, once it has run, then I want to display. So I can display. This is circuit dot circuit is this. This is circuit Q dot quantum circuit 1 is the circuit. Now draw circuit dot draw output MPL. So this is what it is. Now I can change it. I can say it is 2 and this is 2. Suppose I want to create 2 qubit systems and then store the results in 2 bits. Now I will write 2 2. So if I do this, then it runs, and after that, if I want to see this, I get this. See, now Q0, Q1, and there are 2 classical bits. Now suppose I want 4 qubits and 4 classical bits like this, and I can do this and see I've got 4 qubits and 4 classical bits. So this is kind of, I am telling how many qubits I want. So Anirudh asked that which file bits are used right now. Is it? Wait a moment. Is it in inbuilt or did he write all by himself? So it is not inbuilt, and I did not write it all by myself. I mean, it's something that we write all. I mean, in our group. So we write quantum things, right? So these are the beginning. And we will share this whole workbook with you so that you can do experiments and all. So best way to do it, to spend time on it, to experiment. I'm also doing that. My students do that and all that. Now, Sumanto God, thank you. Siddhartha says, I am grateful to you. I am also grateful to you. It's like, you know, it's always nice if people listen to something that we have done. So we keep on doing it. Is fun. So see, it is like this. So now let us scale back. Just write 1 and 1. So it's kind of getting used to it. So see, it is kind of getting used to it, because there are new sentences, new words, and like that. So although we know that object-oriented way of looking at these things, but still, it becomes difficult. For you, it may be difficult, and for me, it is more difficult because I am an older guy. I'm a very old man, and for me, learning a new trick is a little difficult. Okay, so see, I go back to circuit. So circuit. So now see, this is a circuit. All right. Oh, to run, it is shift enter, shift enter. So you go here to run, usual this Jupyter Lab kind of thing, shift enter, it runs. Even these are the, this, what is it called, this markdown thing. So they are also, this is what you write, then shift enter gives you the compilation. Then here is Jupyter Lab kind of thing. Okay, so it's shift enter. So now you see I am using qubit Q and this classical one. All right. Now what we are doing now? So now we are now see it is you write like this. So when you write like this on the markdown, you have to it's actually like Jupyter Notebook. So you write these hashes, then write adding gates to a quantum circuit. This can be done by using this circuit get qubit command and gates and all that. And when you write shift enter, then you will get this nice kind of things, right? So it looks so nice. And then you come here. Now see, adding a NOT gate. I am adding a NOT gate here. So see, adding a NOT gate, that is an X gate over here. So you do like this. All right, so we have added NOT gate. So what I have to do? Circuit. What is circuit? Go back here. This is my circuit. And on this circuit, I am invoking a NOT gate. So that is why circuit.NOT. And when I invoke the NOT gate, then that will ask me. So that will ask me on which qubit I am going to apply this NOT gate, and that is a 0th qubit. Now let us do it in a little different way. Now suppose I open up 2 qubits and 2 classical bits. Let us see what happens. 2 qubits and 2 classical bits. Okay, the circuit ran, and therefore I have to run this. So 2 qubits and 2 classical bits. And now let us suppose that I want to apply a NOT gate on the, or apply a NOT gate to the second qubit, that is qubit number 1. So my first qubit is qubit 0, and my second qubit is qubit 1. If I do this, see, this is happening. This remains as it is. Now suppose I want to do something weird. Now suppose I say I will apply a Hadamard gate on the first qubit. See, Hadamard gate on the first qubit, and unfortunately you get 2 NOT gates because it ran twice. So I have to refresh this matter. I have to again do this. I'm creating a fresh circuit again, and then I'm coming over here. Yeah, see, I have this to be specific. Now I'm applying again. Now I have got what I wanted. So I've got HX, this kind of thing. Now, so this is what we have over here. And now see, I will scroll down, and I'll scroll down to the QSim simulator, and I'll scroll down like this. There are other gates are over here. Now this Hadamard is over here, and the other kind of rotations. Now single qubit measurement, we have done single qubit measurement over here. Remember, we did that, and for that, this is the state vector simulator. So we go to the QSM simulator. So QSM simulator, for that, I am kind of writing this Okay, so I have applied a Hadamard on this circuit H. So what is circuit H? So I want to modify this. Okay, what is circuit H? It must be somewhere over here. Yeah, circuit H. Yes. See, this is circuit H. For some reason, we write circuit H because we thought that we will apply Hadamard gate to this one. Yeah. So, but we have not. We have done. We have committed there, and there. Let us see what happens here. Yeah, circuit H. I have applied Hadamard on this. In this circuit H over here, circuit H is this, and I have applied Hadamard gate on this. I've got applied H gate, X gate on this, so I got this and like that. So that circuit H is this. Okay. So I have applied Hadamard gate on this. All right. Now the point is that, so now I have the circuit H, and with the first qubit I have applied the Hadamard gate, so it is like this. All right. Now this is something that we did the last time. So I am applying a measurement. So measurement is like that. So something got messed up. So let me do like this, and then yeah. So we have the measurement. This is what's happening to show the superposition. Now we have to scroll down to see what happens in the entanglement for 2 qubits. So this is 2 qubit states, and now see. This is what's happening. So for this, I have to define a circuit. So this is again circuit. This is Q dot quantum circuit to 2. So what I am doing, I am opening up 2 qubits and 2 classical bits. And then if I let me comment out all the things over here. This is what I have. And let us suppose I comment out the measurement also. Yes. So this is what I have. So this is the effect of 2 qubit and 2 classical bits. So this is what I have opened up. And if you go back to my, you will see my slides. So you will see that first I applied Hadamard to the first qubit. If I have here Hadamard to the first qubit means the 0th qubit. So circ.h. Circ.h is involving the Hadamard, and that thing is asking me that on which I will apply myself. So I am within parentheses when I'm writing 0, so that means that you apply yourself to 0. So if I do this, it has applied itself to 0. So after that it is C0. In the C0, the notation is Cx. So circ.cx, that is the C0 gate, and that C0 gate is controlled by the 0 and target is 1. It is controlled by 0 means the first 0th qubit is controlling that. If it is 0, if qubit 0's value is get 0, nothing happens. If qubit 0's value is get 1, flip. What will flip? Qubit 1 will flip. All right. So I have to invoke this circ, that is circuit.cx. I am invoking this. Again, shift enter. I have got this. Once I have got this, then actually I have created the entangled state. Now, how will I know it's entangled state? For that, I have to measure, and I have to do the measurement. So if I do the measurement, thing like this, then I am doing this. Okay. So see, this is what is happening. So in the back end, I have got QSim simulator, and then I am doing this. Yeah. So this is the measurement. I have put the measurement, but I have not run this program. So this is the circuit. It is measuring this, storing in the 0th bit, and this thing is storing it in the first bit. So these are the classical bits. So I have built it. Now after that, I have to invoke my backend. So if I am doing on Qiskit, my backend will be QSM simulator, or if I want to be run it on the actual quantum machine, I can also do it with my that whatever is called that token, that API token, and I can do that. But otherwise, to make it fast, I will use it on the simulator. So this is the backend simulator, and then I have created a job. So q.execute, or I'm executing that. Qiskit is execute. What to execute? I'm executing the circuit that I have created. So I have created this circuit with all these things. The circuit is getting changed. It's an object. It's getting changed. So after that, I am creating the circuit. Which backend I am using? QSM simulator. That is my backend. So backend is here. I have specified the backend. So this backend I am using. Now shots. How many times I am going to apply this? If I am going to apply it only once, so I will get a single result. See, suppose let's see what happens if a shot is 1. 1, it is giving me 1, 1. If I take another shot, 2, I am getting again 1, 1. So see, if I apply, so it's like a tossing coins, right? So if I put 4, now see, even after 4 tosses, it got separated. 2 times I'm getting 0, 0 state, 2 times I'm getting 1, 1 state. If now I get 16 times I'm doing this, then see, 9, 7. These are very small numbers. So 9 times and why? Because it's a simulator. So it's actually running. It's not computing probabilities. If you compute probabilities, you will get 0.500, 0.511, but it's a simulator. So if you do it, let us say 160 times, see, it kind of divides it more or less. So in order to do computation, I have to do it quite many times. Then I'll see that I'm getting something like this. So if I get some result like this, then suppose I do not know the state, but I have a 2-qubit state and I am measuring it. My measuring process is this. And if I'm getting something like this, then I will kind of say, probably it's an entangled state. Probably it's an entangled state. I can never know a state completely. All right. So that is what we have come to. We have created an entangled state. We have learned what are 2-qubit states. We have learned about Kronecker product, which is called tensor product, and nowadays, and we have also learned how to create a circuit and implement that circuit, run that circuit on QSM simulator, and kind of verify that it is indeed an entangled state. So that is where I stop now, and I'll take questions. Yeah, so chat is open. Yeah, circuit measure need 2 vector inputs, because I have to say that which qubits I am measuring. There are 2 qubits. So the first vector is giving me the number of the qubits that I am measuring, and the second is telling me where on which qubits I am going to store them. Yeah. Sanjay Kumar asked that, can you explain circuit measure line? 0, 0 belongs to the measurement 1. Can't follow this. By why 9 times Oh yeah, so Sonakshi Saha said why 9 times 00 and 7 times in the case of 16, because you have 16 shots and these are actual machines. So the whole thing is non-deterministic. So you will not get 8, you will get, so although your probability of obtaining the K00 state is, probability of obtaining the K00 state is uh, 0.5 and probability of obtaining the K11 state is 0.5. But when you actually do it, it's very rarely it will be exactly 8 and like that. It will be kind of nearby. Can you what symbols of the gate signify? So can you entangle 3 qubits in the same way as you did for 2 qubits? It should be possible. Some kind of entanglement. We will see those things. We'll see those things soon. But let us first understand 2 qubits. Circuit measure line is not clear. All right, I will make it clear. Yeah, I will discuss this one. I can't say I can make anything clear, but I'll of course discuss it. Yeah, so as I see from the chat, because Devnath says that it is non-deterministic, can NP-hard problems can be solved. I mean, these kind of statements, I mean, these kind of claims are risky. So let us not go into them. Let us see what we can do from a rather straightforward manner, and then go ahead. When we have similar probability results, it is considered, I think I would say that Sudarshini says that, so when we have similar probability results, it is considered entangled. But I will say that, yeah, if you take many shots and then you see that there is some correlation between the qubit states and like that, then I think there is reasonable ground to believe that there is some entanglement happening. One can never be 100% sure though. In this case, yes, so Jyoti wants to say something.
So can you just scroll down and show this plot? Yeah. This is the plot that is on your screen. Just scroll down and show the entire plot. Zoom out if necessary. Yeah, good. Also mute the audience. Otherwise, I'll be echoing.
Yes.
Yes. So I hope I'm audible. Yes. So regarding the question that was asked about the entanglement, so what you can see here is, so yeah, the graph that you see here. Essentially, we have created a circuit and we have simulated the result. The numbers that you see on the bottom correspond. Is my sound clear? Like, is the audio clear from my end? Yeah, okay. So if there is an, yeah, fine. All right, so continuing. So the point is this, the variables that you see on the x-axis of this graph, 0, 0 and 1, 1 correspond to the measurement outcomes. When we are getting 0, 0, it implies both qubits Q0 and Q1 have been measured to be in the K0 state, have been observed, like the measurement outcome corresponds to them, corresponds to the K0 state for both of them. And when I get the measurement output 1, 1 from the classical register, it implies that the two qubits Q0 and Q1 were measured to be in the K1 and K1 states. So as you can see here in this simulation, whenever we are performing the two qubit measurements, both of the qubits together are becoming K0 or together they are becoming K1. Like I'm never getting the possibility where the first qubit is in ket 0 and the second qubit is in ket 1, or vice versa, where the first qubit is in ket 1 or the second qubit is in ket 0. So in general, if the first, like not in general, in this experiment, what we see is if the first qubit, the measurement outcome is coming out to be 0, then the second qubit will definitely be in ket 0. That is the conditional probability, to use a more mathematically precise wording. The conditional probability of the second qubit being in ket 0, given the first qubit is in ket 0, is 1. Similarly, the conditional probability of the second qubit being in ket 1, given the first qubit is in state ket 1, is also 1. So when this happens, we say that the qubit state is entangled. This amount of probability can be equal. It can be 50%, it can be 60-40, whatever. But when the first qubit goes to ket 0, the second qubit will automatically follow it. So that following aspect is what we refer to as entanglement.
Yeah. So so Preeti asks that, sir, in case of entanglement, the very independent existence of qubit is lost, isn't it? How can we further transform its state? I mean, this is fun. I mean, like this is what happens. Like, as I told you, that even if you create entanglement, then you apply the inverse transform, and you will, they again will be, that entanglement will be lost. So it's interesting. Like, kind of not, everything kind of stays there, but it entangles and then disentangles. These things do happen. I uh, uh, now the point is that Rachna Soni asks a very interesting question, and that is very much close to my heart. She asks that when there is so much uncertainty and probabilistic, then how it will help us to solve hard problems. Now, this is the central question, and this is, I believe, in this 4-week thing. Next week, we will be addressing to this only. Like, we will see that, I mean, like, actually, now I think, I mean, like, at this point, whenever I come to this point, I have a sense of wonder. I ask myself, then look, I mean, we have things where there are so much uncertainty, the circuit is unstable, I mean, in some way, I mean, there's instability, I mean, things don't last forever and all that, and I cannot measure, but what is the use of this? But that is precisely what we will see when we will study Deutsch algorithm and implement Deutsch algorithm on the simulator, and I mean, we will study the mechanism of that. Just give us some time. Yes. Any more questions? Integrity of data. No, those are more tough questions. How can a classical computer give results of a quantum computer? It is really probabilistic, or internal, it is not probabilistic but fixed. This is basically a simulator. I mean, we are trying to simulate the behavior of a quantum computer. The reason is that quantum computer, after all, is a more expensive thing, so it is better to have simulators, okay, and do stuff there, and then we can kind of get the idea that what's going to happen. Now, thank you, sir. Okay, thank you very much, Sanjay. All right, I think these are the questions, and I think I'll stop here. And okay, let us take a 10 minutes break, and then after that, Jyoti will. Yeah. So let's have 10 minutes break, and then Jyoti will come over, and he will discuss the some points. Like we will have his lecture. We will listen to him. All right.
Yes, so I should be starting my session in just a minute. Yes, can you guys confirm if my slides are visible? Good. So let us begin our session today. Uh, needs to stay. Yes. So we hit. The color options for this. Yes. So yeah. Yes. Apologies for the delay in my beginning. There were some technical issues which I had to address. And as you can see now, I also have a kind of writing tool on my presentation. So I shall be making some minor annotations to my slides. Of course, the complete version with all annotation will be shared to you guys. To begin today's session, we shall be discussing multi-qubit transformations. But before we even go to multi-qubit transformations, we shall be talking briefly about single qubit transformations. So first, we shall have a brief discussion about single qubit transformations or single qubit gates. And using that, we will move towards multi-qubit transformations. So, and then maybe try to talk briefly about entanglement. So the aim of our discussion today will be to essentially, as has been the case with the previous week, follow whatever follow up on whatever Professor Gangopadhyay has shown during his session and kind of formalize the notation. So whatever he has used on his side, I will kind of try to reintroduce, but with a more formalized notation set. And of course, since these slides will be provided to you, you guys can use this notation in any further work that you do. So moving on. Moving on. So this is the list of topics. So first and foremost, we begin with a single qubit state that is given as ket psi, that is equal to a ket 0 plus b ket 1. Ket 0 and ket 1 are the basis vectors, the single qubit basis vectors. Now, any linear transformation on this vector space can be written by a 2 by 2 matrix. Now, why are we considering linear transformations? Well, if we have vectors, it is what to say, like implicitly possible to define linear transformations on vectors. So it is kind of a mathematical formalism to see what kind of linear transformations we can define and what kind of properties they will have. So in general, any linear transformation acting on a single qubit state can be written as a 2 by 2 complex matrix, that is A00, A01, A10, A11. All these four elements belong to the set of complex numbers. And now when this transformation acts on ket psi, essentially what we are doing here is matrix multiplication. We have a 2 cross 2 matrix and a 2 cross 1 matrix. So we have a 2 cross 2 matrix here and a 2 cross 1 matrix here. So when these two matrices multiply, the resultant matrix will be a 2 cross 1 matrix, which is also a column vector. So that will be of this form. This expression is true for any linear transformation. Of course, those familiar with linear algebra will also be familiar with this expression. And in order to perform this calculation for any given matrix A, we need to be capable of performing the operation of matrix multiplication. So if we know how to do matrix multiplication, we can perform the matrix multiplication to move from this to this. And going forward, whenever this kind of expression is written, I will say A is acting on ket side. So essentially, whenever I'm multiplying this, when I'm applying the linear transformation, I will say A is acting on side. So that is understood that I'm trying to calculate this expression over here. Okay, so moving on. Now, let us see what happens when we consider the action of A on the individual basis vectors. So when I act this matrix A on the column vector 1, 0, we can do the matrix multiplication and we will see that like it is essentially this row with this column and this row with this column. So we will see that A00 and A10 are the only elements that will be present here. Similarly, when we apply A on ket 1, we will get the column vector A10 and A11. Now, somehow, instead of remembering the matrix as a 2 cross 2 matrix like this, if we can just remember these two quantities, then we can see that A acting on ket psi can be written as small a times A ket 0, small b times A acting on ket 1. Because these two expressions, like if you can compare this to this, they are identical. So essentially what I have done here, it is nothing very complex. What I have done is, instead of performing matrix multiplication, I have performed two specific matrix multiplication operations beforehand, and I'm storing their answer. Essentially, I have done this particular matrix multiplication operation and this particular matrix multiplication operation, and I'm storing the results of that. If I know these two results, then any vector psi, where ket psi, when I'm operating it with A, that is when A is acting on ket psi, if I remember these two column vectors, I just have to add these two column vectors with the respective superposition coefficients or the coordinates. So this approach for operator action only requires us to perform vector addition. We no longer have to perform matrix multiplication because the necessary matrix multiplication has already been performed beforehand. And in fact, in this case, since we are only multiplying it with the standard computational basis vector, the matrix multiplication operation is also not very difficult. When I do A ket 0, I'm taking this part of the matrix. I'm taking this half of the matrix. And when I'm doing A ket 1, I'm considering this half of the matrix. So essentially, whenever you are given a matrix, you can break it into two halves, and the action on any vector A ket psi can be written as a sum of those components. Now these, okay, Shur Singh Rawat has said I'm inaudible. Like, am I audible? Can someone confirm? Someone else from the audience confirm? Okay, loud and clear. Okay, so Shur Singh, please check the audio on your end. And it is all right if you have any temporary issues. This session, as every other session is being recorded and being live streamed. So if you are missing anything now, you can go back to the live stream and revisit whatever topics we have covered. All right. So you know what? Let me just make this box. Oh, yeah, make this box a bit better. So I'm essentially considering this part of the matrix or this part of the matrix. For the purposes of our discussion, now the next part that I'm going to say is not mathematical formalism. It is not like present in any like in this form in any text. Essentially, what I'm doing is I'm defining these quantities as tools of simplification, because I'm aware that many people who attend our courses may not have the necessary background in linear algebra, may not be familiar with these things, or in some case might have studied these topics a long time ago and might have trouble recalling them. So for people who have that difficulty, I'm kind of introducing these things as tools to make understanding a bit easier. For people who are familiar with linear algebra, you can go ahead and skip everything that I'm discussing here and do good old matrix multiplication, which is a reliable tool for understanding all of these concepts. Moving on. Now, since ket0 and ket1 are basis vectors, that implies any state ket psi can be represented as a linear combination of ket0 and ket1. If that is true, the effect of any operator A, I do not care what it is, as long as it is a linear operator, a matrix of the form that was shown before, where all 2 cross 2 matrix where all elements belong to the set of complex numbers, then the action of any such operator A on ket psi can be defined if we know these two quantities. These quantities, I am calling them as actions. This is just a name that I have come up with. This is not, again, as I mentioned before, this is not some kind of a formal mathematical approach. Essentially, I mean, it is formal, but the name here is something I made up. A ket0 and A ket1. If I know these two quantities explicitly, these will be two column vectors, as we have seen before, essentially two halves of the matrix. Then we will know what that particular transformation does for us. So over here, I have listed a set of gate operations that we might encounter in this course. So far, of course, we have seen the X gate. The Z gate, you might have seen it in passing. We will talk more about the Z gate maybe in a slightly different session, more on that later. There is this gate called the S gate, which is closely related to the Z gate. And then, of course, we have seen the Hadamard gate. P5, or like some other literature will call it the R5, the workbook that Professor Gangopadhyay had refers to this matrix as R5. So this is also a pretty standard gate. So now let us see what happens when we apply these gates to a given single qubit state. In order to know that, what do we need to know? We need to find out what will happen when this operation acts on ket0 and this operation acts on ket1. So that result has been presented in this table, as we have seen before. If gate X acts on ket0, we know we get ket1. If gate X acts on ket1, we know we get ket0. If gate Z acts on ket0, we will get ket0. But if gate Z acts on ket1, we will get negative ket1. So we will get ket1, but with a minus sign. Now, what does this minus sign mean? We will see in the very next slide. Similarly, gate S, when acting on ket0, will give us ket0. When acting on ket1, will give us iota times ket1. So how can we see this? By looking at the matrix. Look at this half. So this half is the column vector 1, 0. That is the same as ket0. Whereas this part, the column vector 0, I, is essentially the same as 0, 1, but multiplied with iota. Iota times 0 is 0, iota times 1 is iota, where I is, so here, for those who do not remember, I is the standard imaginary number, which is represented as the square root of -1, or to be more formal, I square. Sorry, be more formal. I squared is equal to -1. So that is what I mean by I. So we get I as, like, we get when S acts on ket1, I get I times ket1. Hadamard, when it acts on ket0, we know we get ket plus. Hadamard, when it acts on ket1, we know we get ket minus. Similarly, P5 or R5, when it acts on ket0, we get ket0, no change happens. But when it acts on ket1, we get e to the power iota 5 times ket1. So these are the actions of the commonly used single qubit gates on the computational basis. So given a basis, these things can be calculated beforehand. So if these things are known, then what can we do? What we can do is essentially calculate the resultant state. So now, of course, people who have been paying attention will know that I've ignored the Y gate. The reason for that is Professor Gambhapadhyay, like earlier, it was shown that Y, this gate, was equal to this matrix 0, 1, -1, 0, which implies when I apply, so if I just look at these two rows in this, like this column, when I apply Y to ket0, we should technically be getting minus ket0, and Y acting on ket1, we should be getting, sorry, minus, not ket0, I'm sorry, made a mistake. We should be getting minus ket1. And over here, when Y acts on 1, we should be getting ket0. However, I have written when Y acts on ket0, we get I times 1. And when Y acts on ket1, I have written it as minus I times 0. So what is essentially happening is I have written like my version in this presentation. Sorry, that spelling. Just erase the thing. Yeah, in this presentation, what I've defined as Y is this matrix. It is 0 minus I 0. So how is this matrix related to this matrix? So let me call this Yj for Jyoti and Ys for Professor Sugata Gangappadhyay. So what is the relation between Yj and Ys? If you can do the calculation, you will see that Ys is equal to iota times Yj, because as I mentioned in the previous slide, I squared is -1. So minus I squared will be +1. That's what we have here. And I squared is -1. That is what we have. So why did I ignore the I? That is because this is the standard notation that is used by physicists. And if we use this notation of Y, then X, Y, and Z together have some nice properties that we will not be using in our course, but nonetheless, it is useful to remember them and maintain them. If we write Y in this form, those properties will get slightly altered. I'm not saying those properties will get destroyed, they will get slightly altered. Whereas if we write X, Y, and Z in this form, like if we keep this form of Y, some interrelations between these X, Y, and Z matrices will be more apparent. So that is the only clarification. However, whenever you guys are, what to say, like if any of you ever refer to this gate in at any point in your work, you can clearly specify which version of this gate that you're using and write that expression beforehand, and that should kind of take care of your problem, take care of any problems that might arise. Moving on. So now, as you can see here, for certain gates, when I'm acting it on a basis vector, I'm getting either the same basis vector or another basis vector, and sometimes it is getting multiplied by a complex number. And in all these cases, as you can see, the complex number that it is multiplying is of unit magnitude. Magnitude of I is 1, magnitude of minus I is 1, magnitude of minus 1 is of course 1, and magnitude of e to the power I phi is also 1. These are all unit complex numbers. So whenever quantum gates act on a basis vector, I will get some vector multiplied by a phase factor. Now, what is the importance of this phase factor? So, as we have discussed at the end of our, week 1, we spoke about a little bit about global phases and relative phases in, the definition of the block sphere. So people who have missed out on that can go back and see those sessions. The slides of that should already be available to you. So let us say I have a qubit that is given to be in ket0 state. Then when y acts on ket0, I will get iota times ket1. Like this is the actual state. This is no longer the action. That is what we should remember. Like previously when I was defining these actions, these are not states. These are just some temporary variables I was using for my convenience. When I wanted to calculate A times psi, then I used these two column vectors as a temporary calculation tool. Whereas over here, this is the actual state of the qubit. So in that case, what we will be getting, we will get iota times ket1, in which case this quantity can be treated as a global phase. And as we have discussed last week, if we have a global phase, we can neglect it because it is not possible for us to detect a global phase by means of single qubit measurements. That is why over here, I'm not using the equal to sign, I'm using the equivalent to sign. Of course, iota times ket1 is not equal to ket1. That is never possible because mathematically they are two distinct vectors. But insofar as quantum mechanical or quantum computational measurements go, there is no way to distinguish between these two states. This has been discussed in last week's session. Because of that, I am saying iota times ket1 is equivalent to ket1. Now, however, if I am applying the same gate, that is the Y gate, to the plus state. What is the plus state? A refresher, ket plus is equal to ket0 plus ket1 by square root of 2, or 1 by root 2 into ket0 plus ket1. This is the state. Now, this is a linear combination, of course. Now, how do I calculate the action of Y on this? Simple. I know what is Y0, I know what is Y1. These two things I have already stored. For our purposes, it is stored in this table. Y0 is iota times ket1 and Y1 is minus iota times ket0. So I will just take this 1 by root 2 factor out as common. I will use Y times Y ket0 and Y ket1. I will just substitute those values directly in here. Now both of these are appearing with phase factors. But now I should not neglect them. Now what I should do is, I should now remove the phase factors commonly to come out of the entire state vector. What I mean is, this is equal to iota or I by square root of 2 ket1 minus ket0, which can further be simplified as Like what I can do is I can also pull out a -1. So this entire thing, this vector can be written as -I/√2 ket 0 minus ket 1. This is possible because again, we are doing vector addition. All of these are valid. Like I've just pulled out one minus sign, the negative sign. Now I know minus iota is a unit complex number that is multiplying the entire state vector. Now this number here is a global phase. And this global phase we can again neglect. So that is why this state is equivalent to 1/√2 ket 0 minus ket 1. I hope this is clear. Please keep this in mind when you are doing certain calculations. Again, when will you be doing such calculations? Pretty soon, within the next 2 or 3 days, you should be at most 4 days. You will be getting some workbooks and worksheets, how they will be shared with you and how you will have to do certain exercises and send back to us. Those modalities we are in the process of deciding. Once they are decided, we will let you know. So when you are doing such calculations, please remember these things. Please be mindful of these intricacies. Yes. Oh, why is 1/√2 not included in the global phase? Well, of course, a phase factor is a complex number whose magnitude is 1. 1/√2 does not have magnitude 1. It is not a phase factor. So again, for people who do not remember what a phase factor is, please go back to my session on last Sunday, and you can revise what was covered. The slides have also been shared, so you can go back and read the slides as well. The phase factors are complex numbers that are of the form e to the power iota phi. So this is what I call a phase factor. I should say equal to. I got the eraser size is very big over here. Yeah, that's inconvenient. So this is what I'm calling a phase factor. And if this angle phi is equal to pi/2, then we will get iota. If phi is equal to minus pi/2, we will get minus iota. So this quantity phi in general can be any real number. However, all possible values of e to the power I phi will be obtained if phi varies from 0 to 2 pi. This has been discussed in the previous week's session, so I'm not going into any further details. Those who have questions, I'm referring you to the previous week's sessions. Moving on. Now, so this is kind of how we handle single qubit gates. Any single qubit gate you have ultimately will be represented by a matrix. Now, observe here, I have not spoken about unitary matrices. I have not spoken about any kind of matrices. The rules that I've defined here is true for all kinds of matrices. And since unitary matrices are also matrices, these rules apply to unitary transformations as well. And all quantum gates are unitary transformations. But since this method is far more general, this was shared. Okay, so moving on to what we are actually going to discuss today. So we shall be spending quite some time on this because understanding this notation and what is actually happening is very important to go forward and interpret both the programs that you may write or the algorithms or quantum computational operations that you might read. So now we have 2 qubits that have been labeled as 1 and 2. Essentially, what I have are 2 qubits, Q1 and Q2. Now, Q1 is in the state ket psi, which is some state vector, and Q2 is in the state ket phi. To distinguish that these are 2 different qubits, you know what? I think right now I will quickly take a 5-minute break and address your questions. I think this is a good point to take a break. and I will take questions. So if you guys have any questions, please feel free to post them on the chat. Like, I'll wait for a couple of minutes. If there are no questions, I will resume with the presentation. Will my comments on the PDF be shared? Of course, they will be shared. I'm going to save the PDF as it is. You don't have to worry about that. Now, why is I considered as the phase factor in the first case and minus I in the other case? That is pretty straightforward. Go to the slide. Here, I is the number that is multiplying with the entire state. The entire state is ket1. And what is the complex number that is multiplying with it? It is I. So I is the global phase factor. Whereas over here, what is the phase factor that is multiplying with the entire state vector? Of course, I can choose to drop I and write the state vector as ket1 minus ket0. But we are usually used to writing a state vector as A ket0 plus B ket1. Like, we always write ket0 first and ket1 afterwards, like it's a practice. So because of that, out of force of habit, I've removed an additional minus sign. Again, nothing changes because whether I take that minus sign out or not, there is no way to physically distinguish between these two states. Again, I reiterate, as vectors, these two are different quantities, but through single qubit measurements, I cannot distinguish between them. That is why up until here, I'm using the equal to sign, and over here, I'm using the equivalent to sign. When I put 3 lines, it means equivalence. So how to generalize these gates to QDITs? Yeah, I know many people are writing papers on QDITs. So let me try to address this question once and for all. While QDITs are nice objects, and so what are QDITs? QDITs are essentially, now I don't want to write this on this slides because they are not particularly relevant to our discussions. QDITs are essentially like qubits, but instead of having 2 states, ket0 and ket1, they can have multiple levels. So if I'm talking about qtrits, it will have ket0, ket1, and ket2. We can have like 4-level objects, we can have 5-level objects, and so on and so forth. These are very nice to define. These are mathematically very satisfactory objects, but there is a reason why, and even classically, it is possible to create DITs. Like, we can have a 3-level logical unit, we can have a 4-level logical unit, and whatnot. But there is a very important and good reason why modern day computers, no matter how good they are, fundamentally use only bits. The reason is, when we have only 2 distinct levels per unit of information, controlling it and resolving the data will be much, much easier. Now, if I'm using a 3-level system, then I need to take care of 2 thresholds in order to see if my data stored is, of values, not 2 thresholds. In fact, we'll have to consider 3 thresholds to see if the data is stored in state 0, state 1, or state 2. This, automatically invites a greater potential for errors. And therefore, control and maintenance of data stored like this will be very cumbersome. Bits are simple objects, they are easy to manipulate and easy to control. Any behavior of QDITs or trits or whatever can be similar, like in the classical domain, can be represented through bits. Similarly, any behavior of QDITs can be modeled through qubits. Qubits are the most elementary object for storing information on a quantum computer, and they are also the most easily controlled. That is why our discussion here is for qubits, and that is why I personally feel that qubits are enough. QDITs, of course, the mathematically curious can define them, but ultimately, in the long run, building them, maintaining them, and controlling them will be a huge headache. The smaller the moving parts of your machine are, the easier they are to control. Like, the more intricate they get, the other way around, the fewer moving parts we have, the easier it is to control a particular device. So QDITs, in general, physically might end up being very cumbersome objects to handle. So how can these things be generalized? The generalization is just straightforward linear algebra, to answer Varsha Tiwari's question. Can I show the previous slide once again? So I suppose by the previous slide you mean this one, the tables. So again, I do not know what you wanted to know in this slide, but again, all these slides will be shared with you guys. So you'll be able to, I mean, this will be shared with you, so you will be able to see them. Dr. Kusumlata Agwal has asked, has the content for week 1 been shared? Yeah, been shared? Yes, it has been shared. What is the meaning of all quantum gates are unitary transformations? So again, I've noticed that some of your conversations like that you have had among yourselves in the chat has alluded to these topics. Right now, I am not addressing them in this session because of time constraints and other limitations. At a later point, I will say why all quantum gates are unitary transformations. Right now, it is not necessary for us to understand quantum computing, but we will try to have supplementary sessions and those things. Details of them we will let you know. And rest assured, in one form or the other, we will address all of these questions. Yes, so the link for the course material has been shared here. This is a GitHub repository which will contain all the relevant material. Later on, we'll also try to segregate this and keep the codes, presentations, and everything separately. Right now, this GitHub contains everything that is being shared in this course. Can we use ZX calculus for phase? To be honest, I probably don't know or don't remember what ZX calculus is. So maybe it can be used. I don't know. Maybe you can tell me what ZX calculus is later, and I can tell you whether it can be used for phase calculation or whatnot. And can we can write that as a plus state. I don't know which one you're referring to. If you're referring to the result of the operation, no, this is not the plus state. This is the minus state. Yeah, so that seems to be the questions for now. So again, I'm stopping the Q&A. I'm going to move on with the session. So moving on. So yes, now we are looking at the product states or the products of state vectors. Now, what do I mean by products? So far, we have seen two kinds of products. We have seen an inner product, we have seen an outer product. We know inner products give us probability amplitudes, and modulus squared of inner products give us, well, thank you for sharing the link, but I'm in the middle of a session. I'll probably see this later and comment on it at a later point. I'll keep this in mind. Thank you, Jagdish Picheguram. Continuing. So we have an inner product, we have an outer product. Inner product gives us probability amplitudes and probabilities. Outer products are used to construct matrices and therefore operators. Now, what other products can we do? Well, as we can see, there are a few more products that we can, of course, define. So the 2-qubit state, now I'm just declaring that can be represented in terms of this thing known as the tensor product. So essentially, I'm writing the tensor product as, so over here, I am introducing the subscript 1 and 2 here to identify that 1 and 2 are physically distinct qubits. Now, this is very, very important. Now, what do I mean by physically distinct qubits? It means that this is the state of a particular physical object and I know which object it is. This is the state of another physical object and I know which object this is. Like these are photon polarization states, then I know which photon, the polarization of which photon is represented by ket psi, and I know the polarization of which photon is represented by ket phi. So this in general means a lot. If I'm labeling my qubits, it means that I'm able to track them and follow them at all points. all points of time. Sorry, all points of time. So I will always be able to distinguish one from the other through some means. I have the means to distinguish them, and I can individually control them. So this is very important to know. So kit psi1 tensor product, is it good to decompose? Okay, now there is a question. Reversible circuits we will come to in a bit. Again, as I mentioned, I'm not looking at the questions. Tomorrow we shall be talking about reversible circuits. So your question should be answered then. Kit psi1 tensor product, like this time symbol in a circle is called the tensor product. Kit phi2 can equivalently be written like this, or I can just lose this and write it as kit psi5. So this implies that I'm writing the combined state of a 2-qubit system where the individual qubits are my slides moving? Like is okay, it's fine. Okay. So continuing, like for people who have slides getting stuck, try reconnecting, or if you are joining with a browser, try refreshing the page. That should usually solve the issues. So this is how I can. These are many ways in which I can write. But remember that this 1 and 2 is always present. Even when I'm writing like this, it is understood that this is the first qubit and this is the second qubit. Whenever I'm performing the tensor product, it is implicitly understood that I have some method to physically distinguish the first qubit from the second qubit. This is important. So that is what I've said. The numbering is dropped with the understanding that this ordering is always kept in mind. So one should not say kit psi1 tensor product kit phi2 is equivalent to this. No, this is a different object. This is a different object. So this is not that kind of a multiplication in the strictest sense. So essentially this tensor product operation is kind of special in that sense. Like it is not a multiplication per se, but although we implement it using the mathematical operation of multiplication, we are calling it a product. But essentially what we are doing, we will see, like what is exactly happening here will become apparent pretty soon. Next slide. So now, how do we define the tensor product operation? So tensor products are in general defined for matrices. So if we have two matrices A and B, then the tensor product A tensor B or A tensor product B can be written like this. So essentially what we do is we take one element of A and multiply it with the matrix B. Take the second element of A, multiply it with the complete matrix B. Take the third element, multiply it with the complete matrix. Take the fourth element, multiply it with the complete matrix. So if I take two 2 cross 2 matrices, so this was 2 cross 2 and this was 2 cross 2, what we are getting is a 4 cross 4 matrix. So a tensor product between two matrices of some size will always give us a matrix of a larger size. Now, what is the physical significance? Someone has asked. You will see it soon. Right now, I'm just defining the mathematical operation so that you guys can perform the tensor products. Okay, so please be patient. So now, this is how we can perform the tensor product operation. This statement I will come to address later. The tensor product, of course, is also referred to as the direct product by physicists. Mathematicians will not be comfortable with that nomenclature. Of course, it is also referred to as Kronecker product for several reasons after Leopold Kronecker. And in general, defining tensor products for arbitrary objects is very complicated to handle. So it is
computationally intensive, even if you want to simulate it, if you want to mathematically represent it also, yes, writing it is pretty simple. But if one has to explicitly calculate tensor product expansions and things like that, it is a laborious process. It is time consuming, and one needs to be very careful when dealing with these objects. Moving on to the next slide. Now, this is true for any matrix. Right now, I've used 2 cross 2 as what to say, like an example, because I can fit it in one slide. But in general, this is tensor products can be taken between any 2 matrices of any sizes. So remember this. So I will write it here. This product, so this is the symbol X in a circle, is defined for any 2 matrices of any size. To avoid further confusion and to not overload you with more information, I am not talking about anything more. Otherwise, we can spend weeks upon weeks discussing the intricacies of tensor product itself, but then it will become a linear algebra or an operator algebra course, and we are not doing that. So it is well out of my expertise and the purview of this course. So we shall not be addressing that. Now it is also possible to do tensor products with, oh, okay, I seem to have made a mistake. This is not 1. This number is 2. No, please stay scratched. Yes. Yes. So yeah, I made a mistake already. I've rectified it. So now we are given 2 single qubit bases. Now, what do I mean by 2 single qubit bases? Essentially, it means that this is the basis for qubit 1. And this is the basis for qubit 2. Mathematically, these are the same column vectors. But remember what we discussed in week 1. These mathematical column vectors and all these things represent certain physical properties, as we have discussed in the very first day itself. Like whenever I'm writing Ket0 or Ket1 or anything, I'm either thinking about the photon polarization, or I'm thinking about some property of some ions, or I'm thinking about some properties of some atoms, or I'm thinking about some properties of some kind of a circuit or some optic system or something somewhere. But it refers to a physical quantity. So when I write Ket0 sub 1 and Ket1 sub 1, these are the physical parameters corresponding to system number 1. When I write Ket0 sub 2 and Ket1 subscript 2, these are the physical quantities corresponding to qubit 2 or physical system 2, the second object. Now, why is this not maintaining? Please stay scratched. Yeah, it's scratched. So now we can construct the 2 qubit tensor product basis. So how do we construct that? We take 0 Ket 01 tensor product Ket 02, which is essentially the tensor product between these 2 column matrices. How do we do the tensor product? It is exactly as defined in the previous slide. I take the first element of the first matrix, multiply it with the complete second matrix, and I will take the second element of the first matrix and multiply it with the complete second matrix. That is what I have done here. I have taken 1, multiplied it with 1, 0. I have taken 0, multiplied it with 1, 0. 1 into 1 is 1, 1 into 0 is 0, 0 into 1 is 0, and 0 into 0 is 0. So this complete operation will give me a 4 cross 1 vector, and not vectors, vector. Yes. So this is a 4 cross vector. Yes. Apologies. Yes, spelling is correct. So now this is how I calculate one element. Now remember, if I'm using 1 here, I have to use an element from 2 here. I cannot do this. I cannot take this kind of a tensor product. This is not allowed. Or 0 tensor sub 1, 0 tensor sub 1. This is not meaningful. Why is it not meaningful? Therefore, now I have to describe what is the meaning of this. So now let us talk about what is happening here. Should we talk about that right now? No, right now just remember this. This is allowed. 0 tensor, 0, 1 tensor, 1, 2 is allowed. Like similarly, if I have 1, 1 tensor, why is this not allowed? I'm saying this is not meaningful. Now, again, why this is not meaningful, I will address today itself, but at a later point. Once again, remember that the order is very, very important. And if I have started this labeling by calling one system qubit 1 and the other system qubit 2, I should not change that labeling in the middle. So once I've set the label, it is best to keep maintaining that labeling. So it is very important that this labeling is very important. So if I drop these things, it is understood that I've previously defined a kind of a labeling and I'm maintaining it throughout my computation. Moving on to the next slide. So now, essentially, since I can only do 1, 2, there can only be 4 combinations. I can have ket 0 or ket 1 here. I can have ket 0 or ket 1 here. So I can have 0, 1 tensor 0, 2. I can have 0, 1 tensor 1, 2. I can have, so the 4 products that I can have are 0, 1 tensor 0, 2. 0, 1 tensor 1, 2, and then I can have 1, 1 tensor 0, 2, and I can finally have 1, 1 tensor 1, 2. So I can have only 4 combinations. This is what I'm representing by 0, 0. This is what I'm representing by ket 0, 1. This is what I'm representing by ket 1, 0. And this tensor product is what I'm representing by ket 1, 1. How to calculate these individual matrices, that has been defined over here. Follow the same method to evaluate and see what these other matrices will be. Now, over here itself, one thing becomes very clear. This column vector has only 4 elements. Therefore, for people familiar with linear algebra, you will know that the dimension of this space is 4. This is a 4-dimensional vector space because that is the number of coordinates that this vector has. For those who are not familiar with this, since you either ways have not read linear algebra, you can trust me when I say that this is a basis of a 4-dimensional vector space. Since it is a 4-dimensional vector space, the basis should contain only 4 elements, and this basis contains only 4 elements: ket 0, 0, ket 0, 1, ket 1, 0, and ket 1, 1. So now, what are 2-qubit transformations? Like right now, I do not know any transformation. Like in our presentation, in this slide, we have not encountered any gate that can act on 2 qubits simultaneously. We know of the gates that we know are like this. They act on single qubits. These are the only gates we know. So can we define 2-qubit transformations using single qubit transformations? Of course we can. So how do we define them? I'm sorry. Yeah. How do we define them? essentially what we will say is some transformation A is applied on qubit 1 and a transformation B is being applied on qubit 2. So I have my two qubits, qubit 1 and qubit 2, and separately I am applying two different set of transformations to both of them. So in that case, the complete operator, the two qubit transformation, can again be represented using the tensor product, and that will be written as A subscript 1 tensor product B subscript 2. Now, how to calculate this tensor product? That is why I defined the matrix tensor product first, because we would be needing that result. And why did I use 2x2 matrices? Because single qubit operations are all 2x2 matrices. So now I hope you can understand why I chose to introduce this very first. And since this is a linear transformation acting on a 4-dimensional vector space, this will be a 4x4 matrix. Of course, it is a 4x4 matrix. So you can see that even though I have not explained why I am doing this tensor product, somehow mathematically this is forming a consistent picture. So you can trust me that I'm not saying something that is illogical or nonsensical. For now. Now the physical reasoning behind it, I will explain it shortly. Yeah, we still have time for that. So yes, again, ordering is important. A1 tensor B2 as a short form will be written as A tensor B. Again, A tensor B is not the same as B tensor A. Ordering is very, very important. Now I know I've repeated this like some 40 times already, but it is so important. So let us say that ket psi 1 is some, state A ket 0 B ket 1, ket phi 2 is some C ket 0 D ket 1. So this is the same notation that Professor Gangopadhyay used. Now the effect of A tensor 1 B tensor, sorry, A tensor A1 tensor B2 can be expanded using the actions of A and B on the computational basis. So the action of this implies A is acting on psi and B is acting on phi. So what can I do? I can individually act these on these two separately. And how do I do that? I know this by calculating these two elements. And I've given a table for certain like operators. In general, I've also told you how to calculate this. So of course, here the subscripts are present, 1 and 2 are present. I'm not writing them because by now I've repeated myself so many times. I hope you guys understand that the subscripts exist and going forward, they will not appear. So this entire quantity can now be written as a tensor product of two vectors, small a times capital A ket 0 plus small b times capital A ket 1, tensor product with small c times capital B ket 0 plus small d times capital B ket 1. Now this, like essentially, since I've written this as this, we no longer have to calculate A tensor B. We no longer have to calculate that 4x4 matrix. Now this entire matrix multiplication operation has reduced into vector addition over here, and after that I only have to take tensor product of column vectors. So this approach, like especially if you are trying to do computational simulation, is much more efficient computationally. So people who want to write their own programs for simulating quantum gate operations and things like that, this kind of a representation will be very helpful for you. Let me cover the examples and then we will take a brief break and then we will have another 15 minutes of session. So first, now let us look at some examples. So initially qubit 1 is in state 0, qubit 2 is in state also in state 0. So I have 0 sub 1 and 0 sub 2. Now X gate is applied only to the first qubit and the second qubit is left as is. No transformation, no gate operation is applied to the second qubit. So now what is the combined transformation? To the first qubit, I'm applying the X gate. The second qubit, I'm not applying any transformation. When I'm not applying any transformation, it is the same as applying the identity transformation. The identity transformation will not change any state psi. I times psi is psi for all psi. So this is the operation on the first qubit. This is the operation on the second qubit. So that is x tensor I. Now I don't have to calculate x tensor I. All I have to do is evaluate x0 tensor I0. I have told you I times psi is psi for all psi. So I times 0 is ket0. Now what is x0? Again, jumping back a few slides to this table, I know x0 is ket1. So moving back, x0 is ket1. So this thing is ket1. Oh, why am I saying one thing and writing another? Yeah. So this is ket1. So the final result is ket1 tensor ket0. But again, I've told you that this can be combined. Therefore, the resultant state can be written as ket10. Similarly, if our initial state is in ket minus, the first qubit is in ket minus and the second qubit is in ket1. And if the Y gate is applied to the first qubit and the P5 gate is applied to the second qubit. So yeah, here I've mentioned that P5 is the same as the RZ phi gate in Qiskit. This we shall see more as we start doing more and more Qiskit workbooks. So at this point, I would like to comment the reason why we have not started doing programming right off the gate is it is also true that many of you might not be familiar with the programming aspects. So to teach you two new things at the same time will be very confusing. So first, we wanted to get the theory through so that you guys will at least understand what is happening. And after that, we will start the practical aspects. We will take our time, we will move slowly and steadily. So soon we shall be talking more and more about programs. And the content and the math in the slides will be reducing gradually. So now the combined operation can be written as y tensor P5. Again, I do not have to calculate the operations. What will essentially happen is like y acting on ket minus, this is what is happening. So I'm just substituting y0 as iota times 1 and y1 as minus iota times 0. There is already a minus sign here. So minus and minus will combine to give me plus. So I will have an iota common here. I'm pulling that out. That is tensor product with ket1. Because when the P5 gate is applied to ket1, I get e to the power I5 times ket1. You can, I mean, it was shown in the table. Later on, when you get the slides, you can go back and see that. Of course, you can also see this slide then. So what we will get is iota times e to the power I5. This is also a unit complex number. And therefore, this is a phase factor which can be neglected. So that's what I'm saying. So this is the global phase that can be eliminated. So the resultant state is 1 over root 2 ket01 plus ket11. So this is what is happening when I'm applying these two gates to these two qubit states. So the final example is the Hadamard transformation. So I'm starting with two qubits, both in ket0 state. So psi1 is ket0 and chi2 is ket0. And the Hadamard gate is applied to both of them. So what we have is H tensor H acting on 0 tensor 0. The result can be written as H acting on 0 tensor H acting on 0. Now we know H acting on 0 is ket plus, which is represented as this. And the second for the second qubit also the same vector is written. Now we have to take the tensor product of the combined thing. Now this tensor product operation here, as Professor Gangopadhyay explained before, it's the same as multiplication. Essentially, I will take all combinations from here to here. So I will get 0, 0, 0, 1, 1, 0, and 1, 1. This 1 by root 2 and 1 by root 2 will multiply with each other. So I will get 1 by 2 times ket0, 0 plus ket0, 1 plus ket1, 0 plus ket1, 1. So now each of these state vectors has the coefficient half. Just as a quick curiosity, let us see what this quantity is. 1 by 2 squared plus 1 by 2 squared plus 1 by 2 squared plus 1 by 2 squared is, this is, yeah, thank you for doing the mathematics. So this is 4 times 1 by 4, that is equal to 1. And why did I calculate this number? This is actually the norm of this vector. So even though this is a 4-dimensional vector, it still has a unit norm. Therefore, this is a unit vector. So this is also probably some kind of a qubit state. What kind of a qubit state it is? It is a 2-qubit state. Now, single qubit states were vectors, unit vectors that belong to the space C2. 2-qubit states are unit vectors that belong to a different space. What space that is, we will see tomorrow. Tomorrow, I will probably do the first session to continue this discussion because today we've kind of overshot our time. So I'd like to spend more time listening to your questions rather than teach you more new things. So tomorrow I will begin briefly with a 20-minute presentation and I will let Professor Gangopadhyay continue. So remember that when the Hadamard gate acted on a single qubit, it gave us equal superposition of Ket0 and Ket1. That is, probability of measuring Ket0 was half and probability of measuring Ket1 is half. Now here, what do we have? We have an equal superposition of all these 4 combinations. Ket00, Ket01, Ket10, and Ket11. And what is the probability of measuring each of them? It is 1 by 4, which is 25%. So each of the basis elements are equally likely to occur if you perform a measurement with respect to this basis. What is this basis? I will discuss it first thing tomorrow. Now, just for the sake of curiosity, if somebody wants to construct this 4 by 4 matrix and this 4 by 4 column vector, how do they do it? Well, we do it like this. We take 1 by root 2 and 1 by root 2 times this, 1 by root 2 times this, 1 by root 2 times this, and minus 1 by root 2 times this. So the entire matrix, I've done the multiplication, will look like this. So Hadamard tensor Hadamard is a 4 cross 4 matrix whose elements look like this. And once we get this, we can multiply it with the corresponding 4 cross 1 column vector to get the resultant 4 cross 1 state vector. So this is how 2-qubit transformations can be seen as matrix operations. So with that, I will finish the instruction part of today's session. However, I would like to spend around the next 15 minutes, 10 to 15 minutes, taking your questions. If you have any questions, please post them in the chat. When will the QSim session be? So again, the reason we have not spoken about QSim is the same thing that I mentioned before. A significant part of our attendees may not be familiar with Python programming itself. So, and on top of that, they are learning to write Python programs about a subject that they have very little knowledge about. So for that reason, we first want to introduce the basics of the subject. Then we will talk about Qiskit simulations. QSim is essentially a modified version of an older Qiskit library. So knowing the basics of Qiskit will help you better understand the functioning of QSim. So we will be doing a little bit of Qiskit for now, for this week. And pretty soon we will move on to QSim. So maybe tomorrow itself, and no guarantees, but definitely next week QSim sessions will begin. By then, how access to QSim will be provided to the attendees, all of those things will be decided, and we will let you know. So this is in response to a question from Dr. P. Rajesh Kumar. So Hilal has asked, what is the physical significance of the tensor product and the matrix product? So as you can see, the tensor product is not, I'm not multiplying two matrices here. Like, I mean, I'm technically multiplying two matrices, but this is not matrix multiplication per se. What I'm doing here is now this tensor product operation is representing a new object. Now, previously, the Hadamard gate was a single qubit gate applied to a single qubit. Now, this Hadamard tensor Hadamard, this 4 cross 4 matrix is the actual representation of the 2 qubit unitary transformation that is being applied to the 2 qubit state. The reason for this will become more apparent when we talk about entanglement, which is what I shall cover first thing tomorrow. So, yeah, I know I told I will talk about the physical significance of this today, but since we have overshot the time duration, I don't want to intrude into the lunchtime of people. So I will stop today, but tomorrow I will begin first thing. Okay, so the next question was how to know when to apply what gate for the result we define. Oh, that this is a question from Preeti. Well, that's the whole point of this course. Like right now, we'll have to teach you what the gates are. I mean, first we need to teach you what are all the gates and what they do. Then we will teach you how to use those gates to perform operations. It's just like learning classical logic. First, we will have to define AND or NOT, XOR and XNOR NAND gates. And then we shall teach you to combine those gates and perform full adders, up adders and things like that. So similarly, we shall be doing equivalent things here. We are teaching the basics here. The notations are being clarified. Pretty soon, we will teach you how to convert this into mathematical operations and how to use those mathematical operations to implement elementary algorithms. The tensor product of two gates. How can we show that gate 1 only transforms Q1 and gate 2 transforms only Q2? So that part is taken care of by our notation itself. As you can see, this combination here for the basis vectors, it automatically gave me 4 basis vectors required for the 2-qubit system. So this notation implicitly gives us the actions on the individual basis. That is why in this slide over here, I'm able to write this. When H tensor H acts on 0 tensor 0, I am saying it is the same as H acting on 0, tensor H acting on 0. This is a property of the tensor product itself. So what I've written here is an implicit property of the tensor product. And this is not only true for 2 single qubit systems, this is true for, in fact, any 2 vector spaces. As long as the first operator acts on the first vector space and the second operator acts on the second vector space, this tensor product expression is valid. So how do we know that how can we show? It is shown by the definition of this product itself. Any linear algebra textbook will provide the answers to this. But again, if we go into all those details, this course will become overlong. That is why we are skipping those details. We will try to give some supplementary information for people who are interested in knowing. However, whatever we are mentioning here, you can trust us. Like at the very least, I can claim that both me and Professor Gangopadhyay, we are reasonably competent in linear algebra. So QSim login, of course, if you are working on QSim, you will get QSim logins. Modalities of that, we will tell you soon. Are the output of Hadamard stored in classical bits or another qubits? So when the Hadamard gate acts on the qubits, okay, so this is a nice question from Siddharth. I'm going to give you the answer now, but I'm not going to explain it. I will explain it later. So please don't ask for explanations right now. When a gate operation is applied on the qubits, it changes the qubits themselves. So whatever change happens is stored in the same qubits. It is not moving to another qubit. In fact, the information never moves from one qubit to another qubit. The information always stays in the qubit. The gate operation is applied on top of the qubit. Measurement results are stored in classical bits. This is the answer to your question. Now, how this is happening, why this is happening, we shall see it soon. Okay. For now, kindly take this answer and be patient. Oh, QSim access is already given in the email. Okay, so Vikas Devnath says that this is the case. So people who are wondering about the QSim logins, please check your emails. You should be having that. Harshit Pal is saying the previous lecture PDF is not available. Like I personally uploaded it to the Git repo. It should be there. Okay, after this Q&A is done, I shall check it. And if there are any issues, I shall rectify it. If you're having any other issues, you can try, what to say, like maybe someone in the chat can privately respond to Harshit regarding how to access the lecture material from GitHub. The YouTube links, to the best of my knowledge, will be available, it will not be made offline. Like we'll try to keep it on forever. And different versions of this course have run before as well. So at a later point, we will also share the playlist links for them. So you will have a good chunk of materials from which to which you can listen. So multiple qubit states are equally divided into number of available basis states to keep the normalized form. This is a question from Jagmar. Yes, in this case, when I'm applying two Hadamard gates, that is what is happening. To keep the normalization, yes. If I'm applying some other transformation, they may not be in equal superposition. They can be in some unequal superposition also. Okay, so wow, nice name. Subrabharati is asking how can something be in superposition in many states at once? So I'm going to just do some doodling. So let me just, oh wow, why haven't I done it since the beginning? Why was it in the page fit option? It should have been in the fit width option. I apologize for that. Going forward, it will be maintained. So see, forget quantum mechanics. So this is in reference to a question from Suprabharti asking, how can something be in superposition? So consider we have the XY plane, the real XY plane. So I have the X-axis and I have the Y-axis. There is an object here that is moving in this direction. So it is going from point A to point B. So it has moved from point A and gone to point B. Now such things happen in real life. So this motion from point A to point B through projection can be said that it has moved a certain distance delta x along the x-axis and a certain distance delta y along the y-axis. So this is perfectly possible to mention. But when the object or body is moving along this line, it is actually, the position is simultaneously changing in the x and the y direction. So at the same time, the change, the velocity is a superposition of an x component and a y component. So this is exactly how superposition in quantum mechanics also happens. Two physical properties are actually vectors in some hidden, not hidden space, in some kind of a space. Since they are vectors, it is possible to have superpositions of them. Velocity is a vector, position is a vector. I can have superpositions of velocity and position. That is classical mechanics. We all accept it. In fact, we behave according to it. Our vehicles move according to this rule. We move according to this rule. The planets, stars, everything move according to this rule. Similarly, at the microscopic level, and in many cases macroscopic level also, many physical quantities also have this kind of a behavior. And because of that, superposition, like existence in superposition, is possible because some underlying property can be represented as a vector in some space. I'm not saying the property is a vectorial quantity. No, the property can be a scalar, but the representation of that property is a vector in some space. This is what people refer to as, the Hilbert space, or people who are being more rigorous will call it the rigged Hilbert space or something like that. Those are mathematical constructions. Essentially, in a certain construction, if you can represent the existence of a physical property as a vector, then superposition is an automatic consequence. So the superposition, it is happening in nature. How it is happening, we don't know. Why it is happening, we can't say, because that is how nature is. We just have to accept it. How are we representing it? We are representing it using vector notation. Same as is the case with classical mechanics. So that's question I've already answered. From Samarka Banerjee has asked if results from qubits are stored in a classical computer, then speed is constrained by the classical computer. How is quantum computer beneficial then? This question will be explicitly addressed at a later point. So I'm kindly skipping that for now. The Python notebook file, yes, will be shared. Do not worry, it will be shared. Every piece of material that we are presenting here will be shared with you guys. So like, we have made sure that all the material here is either sourced by us or necessary, licenses or everything have been procured for everything that is being presented. So we can share it openly with as many people as we please with zero conflicts. So, so GitHub repo has all materials and links. QSim login is also working. Okay. Thank you for the comment, Mirza Amirbhai. Dear all, if you're okay, so this is from ICA. Okay, fine. So they have given all that information. Oh, so the questions has actually stopped. So I don't have to feel bad that I'm neglecting anyone's questions. So I think I will stop presenting now, and yeah, this should be as good a time as any to end today's session. So tomorrow we will begin and continue with our discussion. Initially, we are taking it slow. Don't worry, we will catch up with the pace, and only what is being covered. Okay. Only what is being covered will be used for your assessment and all those things. So any assignments so far? No assignments have been given. If the assignments come up, you will be made aware of it. Don't worry. Can I refer to any book to start with? Riffle and Polite is a very good book for beginners. The details of that is already present in the older slides. You can look at that, and the PDF of that is actually available online, like through legitimate sources. Eleanor Riffle has a PDF of that book online, so you can just Google it, download the PDF, and read away. So that is that. Yeah, I think we can end today's session. If the people from CDAC have any comments to make, they can go ahead and do that. The title of the book is present in the slides. So kindly go to the slides and look at that. Even the cover page of the book is pasted there. The image is pasted there. So just go there and refer to it. Yeah. Yeah, I think we can end today's session. Thank you all for listening. We will meet again tomorrow morning. So, Ms. Vandana, should I end this call or will you do it?
Sure, sir. So you can end it.
Okay, fine. So, yeah, thank you all for listening. We will meet.
Thank you, Jyoti, sir.